So, the immortal question is, how do we determine how a charged point mass reacts to an electric field around it? Of course, we could use computers to analyze this, but it would be much more fulfilling to do this by hand. We're going to need to set up the problem first. This point mass has a mass of 0.5 grams, a charge of 0.7 microcoulombs, and a position at the origin. The strength of this electric field around the point mass is dependent on the position of the object in question. 1 is added to the previous x value of the position to determine the current x value. The previous z value is scaled by 6 to get the y value, and the z value is determined by the square of the previous x value. It should also be noted that the point mass is isolated. These given values aren't in units we like very much, so let's simplify. Oops, the position is also in meters. Finally, the delta t we'll use is 0.5 seconds. Oh dear, the words are off the screen. We'll start iteration 1 by finding all the forces on the point mass. Because this is an isolated system, the only force acting on it will be the force by the electric field. Luckily, we have an equation to relate the force on a point mass by an electric field. F, the force on the point mass, equals Q, the charge of the point mass, by E, the strength of the electric field. So we'll start filling things in. When we simply solve this out, we get 1, 0, 0, and then scale the whole thing by the charge to get a force vector of 7 times 10 to the negative 7, 0, 0. Newtons over coulombs? Who wrote this? Those coulombs cancel, and so we're left with newtons. Anyways, now that we have that, we can find the momentum of the point mass. Well, for that we need the initial momentum, which is, I'm just going to tell you right now, it's 0.000 kilogram meters per second. Solving that out, we get our final momentum. For the final step of this iteration, let's find the new position of the point mass. After all, this is critical for finding the strength of the electric field in the next iteration. We can use an approximation of the average velocity over the time interval to determine what our displacement is. After a half second, the point mass has only moved 0.35 millimeters in the x direction. We could keep doing this over and over because each iteration follows the same process. But we're only going to do 2. The force acting on the point mass after 1 second now has a z component because there was a non-zero value in the previous iteration of the x component. Accordingly, the point mass has moved ever so slightly in the z direction too, just 0.042 nanometers. In the x direction, however, the point mass has moved a whole 1.05 millimeters, but there's still no movement in the y direction. Iteration 3 will be done in the exact same way as 1 and 2. Oh, for crying out loud! You could just start a new line. Thank you. After many messy calculations, we have found that in 1.5 seconds, the point mass moved 2.1 millimeters in the x direction, a very small fraction of meters in the y direction, and a slightly larger fraction of meters in the z direction.